Good evening, good evening. This is your Captain Shreyas, and you are on the Vedantu JEE English channel. Welcome to the Noob to Sigma 5-day challenge, and you are already on to the next day. In fact, actually, day 4 of the challenge. Today, we are going to do semiconductor devices and logic gates, all the high weightage important concepts revision, along with lots of practice. So, you know not only what is important, what is going to come, what kind of pattern of questions are going to be asked, but also you revise the theory along with the application and see me solve the questions. It's just a 1 hour class. So 1 hour classes, 3 such classes per day: physics, chemistry, mathematics, 15 classes in this 5-day challenge. If you do this topics and you practice these kind of questions thoroughly, you have that ability to clear JEE Mains and qualify for JEE Advance, right? So that is the intention of these classes, to make you aware, to make you revise, to make you see, and also help you understand and apply the concepts. So if you have not yet subscribed to the Vedantu JEE English channel, please do that right away, right now. And do not forget to mark your attendance right away, right now for this session by liking this video. Hi Vignesh, Nisha, welcome back, man. Hello, Gubil, Dharnesh, Mad Max, welcome, Zalim, Sweta, everybody out here onto the channel. It's time to begin the lecture, right? So let's start. And by the way, I hope you have liked the session, which is going to pop up just in a matter of 2 days, 5th November, 6 o'clock. The most awaited session for these, days or weeks. This is something which everybody will be looking forward to. So make sure you are on to the live section of our channel, and you will find this particular session which is lined up already, and already many students are waiting for it. Make sure you have liked, mark your attendance for the launch of Sigma Crash, right? And from today's session, remember, all the PDFs, everything will be available in the description box. All right, and do not forget to like this video and subscribe to the channel, right? Cool. Let's begin with the class, right? Starting off with the first concept, where we discuss about the N type and P type of semiconductors and band energies. Semiconductors are those devices which have conductivity between metals like conductor, but much better than the resistors or bad conductors which have very low conductivity. One more differentiating factor about semiconductors is they do not follow Ohm's law. They are non-ohmic in nature. And also, you will see the alpha, which is the coefficient of thermal resistance, is negative for semiconductors, meaning when you increase the temperature, the resistance drops down. So these are some of the critical aspects about semiconductors. The conductivity or the resistivity is in between. So for a semiconductor, the resistivity is going to be, I can say, lesser than that of the bad conductors or insulators, I can say. Insulator will have very bad resistivity, and it is uh, the resistance is slightly more than conductors, or basically I can say metals in general. Next important thing about semiconductors, like I said, alpha is negative, meaning when the temperature increases, the resistance will go down. Resistance will go down. And the third thing is it is non-ohmic device. Non-ohmic device in nature. Now you will see, in case of a semiconductor, there is a band gap between the conduction and the between the conduction between the conduction band and the valence band I can say. So if this is the conduction band and this is the valence band, you will see there is a small band gap between them. That band gap is around 1 electron volt. Very small amount of electron volt is that band gap, because if it is too high, then it will not conduct. If it is too low, then it will conduct excessively. It will become like a conductor. So the band gap energy is typically of 1 electron volt. Now that is a pure semiconductor, but you can increase this conductivity or reduce this resistivity by doping it, which is called as extrinsic semiconductor. And there are two ways by which you can dope it. One is where you add more electrons, like for example, arsenic in silicon, where that excess electrons acts like a donor electron and they are readily available for conduction. That is one way, that is called n-type semiconductor. Phosphorus, etc., they are all they are all basically going to add extra electrons. They give donor electrons, so they make that semiconductor into n type of semiconductor. But elements like boron or aluminum, they have 3 electrons only, because of which there is a vacancy of electron. So that is why they are acceptor in nature. So they create a vacancy, they can accept electron. That vacancy acts like a hole, so it is eager to mingle, it is eager to accept electrons, which further increases the conductivity. So n type of semiconductors, please understand, they are made by doping pentavalent impurities. Pentavalent impurities, pentavalent impurities. That's what you will see. And if you look at the energy level diagram, that will look something like this. If this is the energy and you have the conduction band, you have the valence band, this is conduction band, this is the valence band. That extra band which is going to come because of that extra electrons, you will see it will come somewhere over here. Yeah, this is because of those donor electrons, the donor electrons. This is how n type will look like energy wise. If you talk about p type, they come because of trivalent impurities. Trivalent impurities. So the lack of electron creates that vacancy, which is called as a hole, which is called as a hole. In the energy level diagram, if you observe it carefully, you will see that again, you have the conduction band, you have the valence band. This is conduction band, this is the valence band. There is a separate valence band which is now created, separate valence band, which is a separate vacancy which is created because of the acceptor impurities. Because of acceptor impurities. So the energy gap reduces, which increases the conductivity due to these doping or impurities being added. Okay, everyone till this point absolutely clear? Great. Nishdeep, if this is your first lecture or first day of JEE preparation and you're watching Semiconductors, which is the last chapter, plus a series which is meant for more of revision, then I think you are on the wrong lecture, my dear. Okay, I'm not here to increase my views. I will honestly tell you, please start watching these lectures over here. It's there on the homepage of this particular YouTube channel itself. Class 11th preparation, you can see physics, chemistry, mathematics being arranged very systematically. Same thing for class 12. So if this is your day 1 of JEE preparation, humbly requesting you, please watch this. Or if you want, even my older classes are there, the Pathfinder or even the Nurture series. Any of these playlists you can watch. Okay, it's definitely not advisable if you are preparing for the day 1, you watch this class. Having said that, when you put N and P together, it makes a PN junction, and N has more of electrons readily available to conduct. Okay, P has more of vacancies, acceptor places, which act like holes or kind of, kind of positive, but it is not exactly positive. It's wrong to say it is positive and N is negative. It is not right, because actually they are neutral only. So when they mingle, the N type of the electrons from the N side move to the P side where they are ready to accept. So the motion of these electrons from N to P is called as diffusion. So diffusion happens from the N side to the P side. Electrons going from this N side, the electrons will diffuse from the N side to the P side, because of which there is a diffusion current. Current is opposite to the flow of electrons. So there is a diffusion current. There is a diffusion current from P side to the N side. This is called as diffusion. As a result of which, you will see that electrons leaving from here to here makes this positively charged and makes P negatively charged. So there is a voltage difference which is then called as the voltage barrier or potential barrier. Because electrons go here, this becomes negative, this becomes positive. So there is a voltage barrier which is called as the potential barrier. And there is a region which is then called depletion region, because these electrons have diffused from one side to the other side. They have depleted all these charges. So there is a depletion region being formed. And in this depletion region, if suddenly one hole or electron appears, you will see that electron will now go this way. That electron will go exactly the opposite way of how diffusion will happen. So you will see that the drift of the electrons, I think this is exactly opposite diagram. This should not be there because it can be confusing, but this is a correct diagram. Just that P is on the right, N is on the left. Here P is on the left, N is on the right. So it might create some confusion. So forget that diagram for now. You will see that in this particular region, the electrons which are there, they will start moving like this. The electron will start drifting inside the depletion region, because of which you will see an exact opposite current, which is now called as the drift current, Keep this in mind. When you do not connect a PN junction to anything, this diffusion current and the drift current are equal and opposite, and they cancel out each other. So there is no net current in a normal situation. Keep these things in mind. Okay. Having said that, also remember, if obviously in n-type, the number of electrons per unit volume is more than the number of holes per unit volume. In p side are equal. You have not added impurity. Then amount of holes and amount of electrons are equal. So how much is that amount per unit volume is called intrinsic concentration. That Ni square is Ne and NH both multiplied together. So if P type semiconductor is assumed, then NH will be more, Ne will be less, but their product will be constant. If N type is assumed, Ne will be more, NH will be less, but their product will be again a constant. Keep this in mind. Okay. Having said this, also remember the total conductivity of that particular PN junction or whatever it is, that is the conductivity of electrons plus the conductivity of the holes, both of them added together. Keep this in mind. And when you substitute both these values, when you substitute the values of conductivity, right, you can find the total conductivity. You can find the total conductivity of that particular semiconductor. Having said that, also the total current, net current in a PN junction is nothing but the diffusion current and drift current both are opposite. So it will be nothing but the diffusion current minus the drift current. Keep this in mind. Usually the net current is zero when nothing is connected, because both of them will cancel out each other. But when you connect N to negative, P to positive, then it is called forward bias. It will help in the flow of current. But if you connect it in the exact opposite way, that is called reverse bias. It will stop the flow of the current. That gives me the current versus voltage characteristics, which you should know, where if you have, this is the symbol of a PN junction, where this is P side, this is N side. If N is connected to negative terminal and P is connected to positive terminal, this is the forward region. In such a scenario, you will see the drift current will not change. The drift current will not change, but it is the diffusion current which increases. It is the diffusion current which increases, causing a net flow of the current. That is how your net current will flow, because of the diffusion current being increasing, and it breaks the potential barrier. Yeah, it overcomes this barrier of voltage and diffusion occurs significantly. Okay, so that is very, very important for forward bias. But until the potential barrier is broken, there is no significant current in the circuit. That sudden jump only happens after that potential barrier is overcome. So that part in that circuit where current suddenly starts increasing, where the potential barrier is overcome, that particular point is called as the knee voltage in the voltage terms. It is that point after which current starts increasing significantly. Keep that in mind. So current is significantly there after knee voltage in the forward bias. P is connected to positive, N is connected to negative terminal. Diffusion current is the major contributor. In the reverse voltage, in the reverse situation, the drift current actually will not change much, but it is the diffusion current which reduces little bit. The diffusion current which reduces a little bit, the drift current doesn't change much. So there is a small current which is flowing now. There is a small current which is flowing. This is negligible in the case of reverse bias. So in the case of reverse bias, if this is your symbol of PN junction, this is P, this is N. N is connected to positive, P is connected to negative. Very small leakage current will flow. It is negligible. It's as if it is not conducting only. But when the voltage increases beyond the point, then breakdown happens and sudden surge of current happens after a large reverse voltage is applied. Okay, that is only at a very later stage, not at initial stages. This diagram is not at all symmetric, guys. This happens very soon, knee voltage, but the breakdown voltage happens very later on. Second point, this graph is not exactly vertical. This might mislead sometimes. It is not exactly vertical over here. Actually, this is more vertical. So this graph actually looks something like this. After the breakdown, it goes down over here. And this graph basically keeps on going like that. So there is a significant jump. So this is the true nature of the graph. Okay. Cool. This is the current versus voltage characteristics. So that is why we say a PN junction like this, a PN junction mainly conducts in the forward bias and it blocks the current in the reverse bias until you reach the breakdown. So that is why it is like a one-way traffic police who allows current only in one direction. This characteristic is used in making of a device called rectifiers. Rectifier is that device which converts AC voltage into DC voltage, meaning bidirectional current into unidirectional current. Bidirectional current into unidirectional current. So, just 1 second, please. Yes. Having said that, there are two ways in which you can convert that bidirectional current into unidirectional current. One is called half wave rectifier, where out of the complete AC signal, only one of the cycles is converted or used as an output. The other half is completely ignored because the current gets blocked by the diode. So when the current is flowing like this diode is forward bias, it will conduct. But when the cycle is negative cycle, so the current is trying to flow in the anti-clockwise direction, this diode is going to block it. So there is no current outside. So you can see out of the positive and negative cycles, only the positive cycles are going to come. That is why this is called as a half wave rectifier. But in case of a full wave rectifier where you have two diodes, then in the positive cycle, one of the diode will conduct, and in the negative cycle, the other diode will conduct, because of which both the diodes are, taking chances or turns one after the other in conducting, and you're always getting an output. So you can see instead of the current changing the sign of the direction, it is always maintaining the sign. So it is unidirectional. So that is why it is called full wave rectifier, because the entire wave has now been converted into my DC output. Here half of the wave, that's why half wave rectifier. Okay, so let's have a look at some of the questions and then we will go ahead. All right. So here we have the current versus voltage characteristics of a PN junction diode in forward bias. The ratio of the dynamic resistance corresponding to forward bias voltage of 2 volts and 4 volts respectively is in what ratio? Now, there is a small difference between static resistance and dynamic resistance. If you observe this particular graph, okay, let me show it to you over here only. Okay, normal resistance, which is also called as your static resistance, is nothing but voltage at that point divided by the current at that particular point. But the dynamic resistance is nothing but the change in the voltage by the change in the current, the change in the voltage by the change in the current, which is kind of the slope of that graph. So that is one small difference. The original values, if you divide, you get your regular resistance in ohms. But if you divide change in the voltage upon change in current, you get something called as dynamic resistance. So now if you notice in this particular question, the question is on the dynamic resistance at 2 volts and at 4 volts. So if you first talk about 2 volts, this much is the change in the voltage and this much is your change in the current. So the dynamic resistance at 2 volts, which is change in the voltage, which is 2.1 minus 2 divided by change in the current, which is 10 minus 5, but this is milliamperes. So this is 10 to the power minus 3. So 2.1 minus 2 is 0.1, 10 minus 5 is 5. That will make it 10 to the power 3 over here. Okay, if you want, we can also write it as 10 to the power 2 divided by 5, which is 100 by 5, which is nothing but 20 ohms. So dynamic resistance at around 2 volts is 20 ohms. Everyone? Now let's go to the next point, which is 4 volts. This much is the change in the voltage and we notice this much change in the current. So the dynamic resistance at around 4 volts is change in the voltage, which is 4.2 minus 4 divided by change in current, which is 250 minus 200. So, but this is in milliamperes. So multiplied with 10 to the power negative 3. 4.2 minus 4 is 0.2 divided by 250 minus 200 is nothing but 50 into 10 to the power minus 3. If you want, we can take 0.2 over here, swallow one 10 to the power negative 3 with that 0. So it will become 5 into 10 to the power minus 2, which is, take the 10 to the power minus 2 on the top. So 0.2 into 10 to the power 2 divided by 5. That will make it 20 divided by 5, which is basically 4 ohms. So now that we have it, we can find the ratio of the resistance at 2 volts and at 4 volts. So R2 is 20, R4 is 4. So this will be 5 is to 1. So 5 is to 1 is option B. Is that right? Understood how to solve this particular question? Everyone? Yeah? All right. Perfecto. Amazing, amazing, amazing. Let's move to the next question on your screen, and here it is. It says, what is the current through the battery in the circuit shown below? Well, I can say this is the positive terminal of the battery. This is the negative terminal. The positive is connected to the P and the P of the diode, and the negative indirectly is connected to the N side. So both the diodes are basically forward bias. If both the diodes are forward bias, what will happen? Well, it will conduct electricity very easily. The battery will supply the current will reach here, it will get distributed in both these branches and it will again accumulate before again circulating back in the battery. So basically these are nothing but two resistors in parallel. So parallel resistance is 20 into 20 divided by 20 plus 20, R1 R2 plus R1 plus R2. So this will be nothing but 20 divided by 2, which is basically 10 ohms. So once I get that, we can easily find the current. It is the total voltage divided by the equivalent resistance. Voltage is 5, resistance is 10. So this will be nothing but 0.5 amperes. So 0.5 amperes is the third option. That is absolutely correct. Got it, everyone? Okay. So this is how you solve the question because they were in forward bias. If one of the diode, let's say this one was in reverse bias, meaning it was connected in the opposite way, then the current would have just gone through this part. It would completely avoid the reverse bias. In that case, the resistance would have been just 20 ohms, and then the current will be 5 divided by 20. Okay, 5 divided by 20, which is 1/4 or 0.25 amperes. Is that right, everyone? All right. So moving on to the next one coming up on your screen, here it is. Rocket Boy, sir, if I learn new topics, may I take notes or use flashcards? Taking notes right now is not the right move. Using flashcards is better, not for learning new thing, but for after you've read the theory from your teacher's notes or your NCRT or your textbook, then instead of making your own notes or revising or while solving problems, it is when you use the flashcards. Here is the next one. The output voltage in the following circuit is how much? Output voltage, okay, in the following circuit. Well, as you can see over here, output voltage is here. This is 5, this is 5, this is a diode. If some current, just imagine some kind of current will flow over here. Assume. What will be the voltage at this point? It will be using Ohm's law. It will be 5 minus I into whatever that resistance is there. That will also be equal to V out. That will be also equal to V out. And because this diode, if it is conducting in the forward bias, then the current should go from here to here. But then P side should be connected to higher volt. But as you can see, this point is 5 minus something. So you can very well see that the P side is connected to the lower voltage, N side is connected to the higher voltage. So this is definitely in reverse bias. So this point, there is no current at all in this particular branch. So all the current, if at all, should go like this only. If at all there is any current, that current should go like this only. That same current will come here, same current will go like this. Now this is connected to the ground. So ground means 0 volt. Yes, this is 0 volt. This diode will now become forward bias because this is higher voltage, this is lower voltage. So this diode will become, a forward bias, and the diode will have negligible voltage drop. So this point, if this is 0 volt, even this is 0 volt, the diode will have negligible voltage difference. So this will be also 0 volt. So even this point will be also 0 volt. Also, this point will also be almost 0 volt. So this 5 minus IR will be 0 volt. From that, you can find out the current if this resistance is known to me, if at all that is asked, but it is not asked. So hence the output voltage will be negligible, close to 0 volt. That is the answer. Got it? Yeah. Everyone with me? Shall we go ahead to the next question coming up on your screen? And here it is. What do we have? Wow. A complex question on your screen. 2023 it was asked. In the given diagram, V in is given. That means the input voltage is given. The circuit voltage of PN junction diode D1 and D2 is 0.6 volt, the cut-in voltage. Which of the following is the output waveform? Which of the following is the right output waveform? Very interesting question. Let's understand. 0.6 volts is cut-in voltage means what? That is the voltage after which current is significant. Till that time, there is negligible current. So now imagine, as long as the current is between 0 to 0.6 volts or 6 to 0.60 volts or 0 to negative 0.6 or minus 0.6 to 0, these four situations. So if my input voltage magnitude wise is less than 0.6 volts, the current through the diode will be insignificant. First of all, D2, if you take the positive cycle, D2 will be not conducting only. This will be obviously reverse bias. This will be reverse bias. This diode, yes, it is forward bias. this is forward bias, but the current in it is negligible. If the current in it is negligible, think about it. Think about it. Current in it is negligible across it. So whatever voltage you are giving will almost come over here as it is. Will almost come over here as it is, right? I hope that makes sense to everyone. So there is negligible current which is flowing through it. Negligible current flowing through it. So whatever over here also, this current will also be negligible. There is no voltage drop here. So whatever voltage you give here will also be the output voltage. So V output will be approximately whatever is the V input voltage. So the graph will just follow as it is. There is no change. But imagine the situation when the input voltage magnitude wise is more than 0.6 volts. Then what will happen if you take this situation or even this situation? The current in the diode will now become significant. So now in this particular diode, which is still forward bias, this current is large. This is definitely a large amount of current. There is no current which will flow because this is still in reverse bias. So a large current will flow. This current is definitely much, much larger than zero. So because of it, whatever voltage drop is, whatever voltage is given by the input, a lot of voltage will be dropped across the resistance. Hardly anything will be left for the output. This V out will be whatever V in is giving minus that large current into resistance. This term will become significant because current is very, very large. So hardly anything will be left. So this will be hardly anything will be left. I'm not saying it will be zero, but after that, it will stop growing. So after reaching that particular, voltage between 0 to 6 volts, it will stop growing in amount. So I think it will get cut out. I think it will get cut out. So between here to here, there will be no much increase. That's it. And you will see here from 0 to 0.6, zero point 0.6 to 0, 0 to minus 0.6, minus 0.6 to 0, it will be like that. So after that point, there will be no further change in the current or voltage in that particular circuit. That's it. It will get cut out. So I think D will be the right answer in this. Is that right? Clear? Okay. Very interesting question, my dear warriors. Now, let's go to the next question, which is coming up on your screen, which is about choose the correct waveform that can represent the voltage across the resistance of the following circuit, assuming the diode is a ideal one. Okay, interesting. The diode is a ideal one. Very similar to the previous question, but there is a battery over here with a single diode and voltage across the resistance is asked. Now again, take the following idea. This is a AC circuit. So there will be a situation when the current will be between 0 to 3 volts. I have connected a battery of 3 volts. So if our input voltage is like this, then there will be a time when my AC voltage will be between 0 to 0.3, sorry, 0 to 3, my bad, magnitude wise. So this is 3 volts minus 3 volts. And when that is happening, between 0 to 3 volts, when my input voltage is less than equal to 3 volts, which is the voltage of the battery, you will see this point voltage will be less than or equal to 3 volts, but this battery is giving me 3 volts over here. So this diode will be in reverse bias. This diode will be in reverse bias because this is at a lower voltage. This battery is giving higher voltage. Because of that reverse nature, there will be no current only in the circuit. So the current in the circuit will be zero. Because there is no current, what will happen across the resistor? So the voltage across the resistor will be I into R, but this current is zero. So this voltage will also be zero. I think there is one small printing mistake here. Actually, 0 volts, I think either C or D option, one of them. This should be a dotted line, meaning no voltage will be there between 0 and 3 volts. Okay, so there is no voltage absolutely across the resistor. Now, when you have the input voltage more than 3 volts, what happens? This point, the moment it becomes more than 3 volts, actually, it becomes more than 3 volts. This diode becomes now forward bias. Suddenly, there is current flowing in the circuit, which is definitely not zero, which is definitely not zero. And because of that, the voltage across the resistor will be current into resistance. So this voltage will definitely not be zero and will follow the same path as that of our input. So it will just continue. However, my input is growing and decaying. So it will go as it is. It will just go as it is. That's it. So I think somewhere it is missing somewhere. Yeah. And if it becomes negative voltage, then what happens? Let's think about that also. If imagine this becomes positive, imagine if this becomes positive, still it will be in reverse bias only in the negative cycle. This will be in the reverse bias, so it will not conduct at all. So I think this should just go like this. Perfect. So in this particular half, this will be positive, this will be negative, this diode will be in reverse bias. So it will not conduct at all. So I think this will be the right graph. Absolutely. Okay. But other times between 0 to 3, 3 to 0, 0 to -3, it is going to be non-conducting in nature. Okay. So that is the logic behind it. This will be also dotted line. There will be nothing over here. And again, you will see it will begin conducting over here. So the third graph is the right one. Okay. Is this clear? Why this line came? Because when this negative half cycle will start, then you will see it will become into reverse bias. Reverse bias means there will be no current. No current means gone. Voltage will go off. Okay. Cool. Perfecto. Right. Let's go now to the next question. Before that, we have some current voltage characteristics which you should be aware of for different kinds of devices, starting off with a Zener diode. A Zener diode is always operated in the reverse bias. Zener diode is having this particular symbol, always in the reverse bias. That means this will be connected to higher voltage, this will be connected to lower voltage, and it will be always operated in reverse bias in the breakdown region, because in that breakdown region the voltage across that Zener diode is roughly a constant, and when it is constant, that Zener diode acts like a voltage regulator. Voltage regulator. Regulator means no matter what, it bears the fluctuations in the voltage and maintains that constant voltage across that Zener diode. So that is the main application of a Zener diode, to absorb those fluctuations in the voltages and make sure that the voltage across it is constant. This is the circuit diagram for it. So if you are giving in some current and there is some voltage given in, you will see even if the voltage increases or decreases, the voltage across the Zener diode will always be a constant voltage. Remember, this is positive, this is negative. The Zener diode is in reverse bias. Okay, so no matter what, if you sense using a voltmeter what is the voltage, it will always be a constant voltage. That is the application. It is always operated in this particular region, in the breakdown region, because you can see in the current versus voltage graph, the voltage is constant. Next important thing is for a LED, a light emitting diode. When current is passed in the forward bias, current is passed in the forward bias. Yes, this is current in the forward bias. You will see that light will come out of such a diode, and it depends on how much current you are passing, what kind of semiconductor you are using. So that will decide which color is going to come out, and the diode is always going to be operated in the forward bias mode. Keep that in mind. It will be operated in the forward bias mode. Yes, if you increase the current, more color will come out, more current will come, means more intensity of light will come out, but it will not keep on continuously increasing, because there is a limit till which you can achieve a certain brightness, beyond which you will not see that the intensity of light will increase. So there is a limit till which the current can increase the intensity of that particular LED. Having said that, let's go to the next thing, which is a photodiode. A photodiode is the exact opposite of LED, where light falls and it changes the conductivity. And you will see such a photodiode is operated in reverse bias. In the reverse bias. LED is used in your mobile screens, TV screens, so many warning lights, headlights, so many bulbs. They are all going to use LEDs, and different colors are there and useful for different purposes, like red for warning, orange for indicators, white for your home lighting, and yellow for maybe ambient lighting here and there. So those different colors are going to come out of that particular diode, useful for replacement of your regular bulbs. A photodiode is where light falls over it and the current changes accordingly. Now, these diodes are used for sensors, where imagine you have to design a burglar alarm. So if a burglar enters the house, maybe the light falling will change at a space, and because of which a circuit will get triggered and the alarm will be raised. Or you put your hands in a sink where you want to wash your hands, so automatically the light falling on the sensor will change. That will trigger a circuit which will open the valve and water will flow. So those kind of applications where you sense the light falling onto it, and based on that you judge what to do next, whether you have to turn on something, you have to raise an alarm, you have to turn off something. Those applications involve photodiode. And yes, those photodiodes are always in the reverse bias, because small changes in the light can affect decently enough the current in the reverse bias. Once you take it in the forward bias, the current is so large that the fluctuations in the current are not so noticeable. So that's why you use reverse bias, because even a few microamperes of fluctuations in the current can signify any changes in the light falling on that diode. That is why you use the reverse bias. The last one is the not basically a diode per se, but yes, the solar cell, which is again based on a similar principle, where the light which falls on that particular semiconductor wafer triggers those electrons to jump on to the other side, and it enables a current to be established in the circuit, and it is like a photoelectric effect which is happening at the semiconductor level. So think of photoelectric effect with PN junction diodes combined together. That is basically your solar battery or solar cell. Yes, you don't have to bias it, meaning you don't have to connect external battery to it, because that itself is going to act like a battery. Having said that, remember, the voltage and the current will not be continuously increasing or decreasing at all the possible levels. If you take the voltage and the current and you multiply, you will get the power, and you will see that the power will follow this kind of curve, and maximum power is achieved at a certain voltage and at a certain specific current. If the voltage is too less, or the current is too high, or the voltage is too high, or the current is too less, then you will not probably get the maximum power. So there is a balance which is supposed to be struck, so that their product is maximum when you get maximum power out of a solar cell. The current versus voltage graph looks something like this. This is the IV curve, which is current versus voltage. When there is hardly any voltage across the solar cell, the current is maximum. But when there is hardly any current through the solar cell, then the voltage is maximum. So you can see the curve follows this kind of graph, this kind of graph. So where current is maximum, voltage is minimum. Where voltage is maximum, current is minimum. And somewhere over here, you will see maximum power. That means a balance is struck between voltage and current, and you get maximum performance from that solar cell. These graphs are obviously very, very important. Yeah. Good evening, Sigma Roy. Hi, Sumi. Welcome aboard. Yeah. Good evening, Nishita. Let's solve some questions coming up on your screen. And here they are. Mainly statement-based questions have come repeatedly again and again from this particular concept. Which of the following statement is not the correct case of light emitting diode? Not correct about light emitting diode. Okay, light emitting diode, it emits light, remember, and it is always connected in forward bias. Keep that in mind. Yeah. Is it heavily doped? Which is not correct. Yes, it is a heavily doped because you want lot of free electrons and holes to be there, so that more the electrons jump into the holes, that will emit more photons, more light, and the LED's light will be clearly visible. It emits light only when it is forward bias. This is obviously correct. It emits light only when it is in reverse bias. This is obviously wrong. The energy of the light is equal to or slightly less than the energy gap of the semiconductor. Yes, because what happens is, if the electron jumps from higher energy to a hole which is at lower energy, that energy difference is converted into the photon with that amount of energy. So yes, the band gap energy is roughly equal to the energy of the photon which is going to be emitted. It can't be more than that, because where will the energy come from? So A, B, D is correct. So the option which is wrong is C. So the third option should be marked as incorrect. The question is not correct. Please remember that. Okay, be careful, or else you will say A, B, and D is correct. Yes, A, B, D is correct, but C is wrong, which has to be marked. Moving on to the next question on your screen, and here it is. This is purely a graph based question. I'm pretty sure you will be able to solve this very easily. Come on, guys. Identify the solar cell characteristics from the following option. I just told you current versus voltage graph of a solar cell looks something like this. When current is maximum, voltage is minimum. When voltage is maximum, current is minimum, and the graph looks like this. So a similar graph over here is in this particular region. As you can see, option B is absolutely right. Option B is absolutely right. Yes, the graph is inverted. That is because the direction of the current, how it is taken as positive or negative, that decides the sign of the current. So sign wise, if you take, actually this graph makes sense, and that is why it is right. But the shape, as you can see, it is absolutely fine. Okay. Oh, hi Lakshya, welcome aboard. Next question on your screen, and here it is, guys. Come on, I want everybody to spam the answers in the chat box. Consider the following statements. Which of them do you think is true? Okay, let's see. The junction area of solar cell is made very narrow compared to photodiode. This is wrong. Actually, it is made very wide for a solar cell because you want more photoelectric effect to happen, more light to fall, more electrons to be emitted, and you want the transitions to happen in large amount, because of which large current, large voltage can be produced. Solar cells are not connected with external biases. That is absolutely fine, because solar cell itself acts like a battery. LED is made of lightly doped PN junction. That is wrong. It is actually very, very heavy. You want more light to be emitted. Increase in the forward current results in continuous increase. This is wrong. The word continuous is wrong, guys. It will increase till a certain limit, not continuously, certain limit, after which it cannot increase the light intensity. Yes, till a certain limit, if you increase current, light will also increase, but not beyond a certain limit. LEDs have to be connected in forward bias. This is also absolutely right. So B and E, that means my fourth option will be absolutely correct. Is that okay, everyone? Let's go to the next question on your screen. What do we have? Yes, this particular one. The current voltage characteristic of an electronic device is shown in the figure. Which kind of device do you think this is? As you can see, this is current voltage. This region is forward bias. This region is reverse bias. So a diode which is operated in the reverse bias, either it is a photodiode or a Zener diode, because LED goes in forward bias and solar cell is not even biased. So it has to be a photodiode or a Zener diode. Okay. So transistor, solar cell, Zener diode, a diode which can be used as a rectifier. I can see Zener diode over here. So this is absolutely correct. And in fact, Zener diode is operated in the breakdown region, which makes more sense. Yeah, perfectly fine. Cool. Shall we go ahead, guys? Ready for the next question coming up on your screen? And here it is. What does it say? The following circuit, the reading of the ammeter will be how much? If the Zener breakdown voltage is 4 volts. Okay. It is mentioned that the Zener diode, obviously it's in reverse bias. It's in reverse bias because positive is connected to negative or P. Positive is connected to N and negative is connected to P. So obviously it's in reverse bias. So this will be in the breakdown region. So whatever voltage will be there will be exactly that 4 volts. It will make sure 4 volts is the drop across of it. So this and this all are in parallel. Voltage across Zener diode is voltage across the voltmeter, which is also voltage across the resistance of 400 ohms, and that will be current into resistance. So how much is that voltage? It is 4 volts. How much is the current? I do not know. Resistance is basically 400 ohms. So current will be 1 by 100, which is 10 by 1000 of an ampere, which is 10 milliampere, which is also the reading shown by the ammeter, because that same current is going to go over here. That's it. So 10 milliamperes is the right answer. Very nice question. Lot of people, they don't understand how exactly to proceed in this. The concept is whatever voltage is there will be in parallel, so it will be the same. So you measure this voltage, which is 4 volts, which is the breakdown voltage, and voltage is current into resistance. Simple. That will give the answer. Okay, these kind of questions, very straightforward. Moving on to the next question, guys. Come on, figure it out. What do you think is the correct answer to this particular one? A Zener diode with some voltage is used to regulate an unregulated DC voltage. Input of 25 volts, 400 ohm series resistance. Zener current is 4 times the load current. The load current and the resistance are. First thing we'll draw is the diagram. We have an input of 25 volts. So I will show 25 volts over here. That is connected in series with a 400 ohms. So there is a 400 ohms series resistance that is now connected to a Zener diode. So I'll show Zener diode, but remember it has to be in reverse bias, and there is a load resistance. So load resistance will be like this. This is my load resistance. Absolutely. The question is how much is the load resistance and the load current, and it is also mentioned the Zener current is 4 times the load current. So if I say this current is I, then this is 4 times of I. By Kirchhoff's current law, this will be 5 times of I. This will be 5 times of I because 4I plus I will become 5I, and that same 5I current will go over here. Having said that, now we also know the Zener voltage uh, is given to be 5 volts. So this much, the voltage across this element is 5 volts. It is in reverse bias. It's in breakdown region. No matter what you do, this voltage or this voltage will be 5 volts. That means out of the 25 volts, 5 volts is here. How much volts will be over here? It will be 25 minus 5, which is 20 volts. That much volts will be, because 20 volts plus 5 volts will give me 25 volts. Once I have that, 20 volts will be equal to this current into resistance. So 5I multiplied by that resistance, which is 400. From this, we can find that current. That current will be 20 divided by 5 multiplied by 400. So this goes 4 times. So this will become 1 by 100 of an ampere, which is nothing but 10 by 1000th of an ampere, which is 10 milliamperes. 10 milliamperes is only there in one option. So fourth option has to be right. But for confirmation purposes, if you still try to solve it for the resistance, The voltage of 5 volts is that particular current into that particular resistance, which is RL, and I want to find RL. So RL will be nothing but that 5 divided by how much ever that current is. That current was 1 by 100. That current was 1 by 100. So therefore, my load resistance will be 500 ohms. 500 ohms is still my fourth option only. Okay, so that's how you can solve this kind of questions. Perfect. I have kept one homework question for all of you with the answer on the next slide. Very similar question, load resistance, voltage across Zener diode, input voltage, series resistance. Question is find the value of the series resistance. That means you have to find this. Stream kind of logic has to be used. Please solve the question at the comfort of your home, but please make sure you solve it. Okay. And the answer and the solution is there on the next slide, which can be downloaded after the session is over in some time. The link will be there in the description box or even in the comment section. The logic gates, this part we'll also do. OR gate, AND gate, NOT gate, NAND gate, NOR gate. Okay. First of all, let's start with NOT. NOT is an operation which negates the input. So if 0 is coming as an input, it will make it 1, or false will become true. And if true is coming, it will become false, or 1 will become 0. So this is our digital logic, Boolean algebra it is also called. Symbolically, you put a bar over there. The symbol for a NOT gate is this. You put a circle in front, that's it. That becomes a NOT gate. So true becomes false, false becomes true, high becomes low, low becomes high, 1 becomes 0, 0 becomes 1, yes becomes no, no becomes yes. That's what it means. That is a NOT operation when you put a bar over it. Next is the OR operation. OR is symbolized by the plus symbol. The circuit symbol is this one, and the output is a high or a true or a 1 when any of the inputs is 1 or true or high. So 0 or 0 will be 0 because none of them is 1, but 1 or 0, 0 or 1, or even 1 and 1 or 1, they all will give the output as 1 because one of them at least should be high or 1 or true or a yes. That is the meaning of OR. This or that. Either one of them is true, the output is a true. AND gate. Both of them compulsorily have to be true for the output to be true. The symbol is a dot, and circuit symbol you put a D like thing. This is the symbol of an AND gate. So 0 and 1 will be 0. 0 and 0 will be 0. 1 and 0 will be also 0. Only 1 and 1 will give me 1. Both have to be true for the output to be true. Lastly, for your NAND and NOR gate, it is basically the same AND gate. It is the same AND gate, but you put a dot symbol, meaning whatever output you get, you negate it, you invert it, you put a NOT gate in front. Now this A dot B can be also written down using De Morgan's principle as A bar and B bar separate but with a plus. So you can write a NAND gate as a NOT gate of A, a NOT gate of B, and ORing both the operations. This is basically your De Morgan's law, which can be used at many places. NOR gate. NOR gate is basically OR gate, but you are negating the output. Whenever you are getting 1, you are making it 0. Whenever you are getting 0, you are making it 1. Symbolically, it is nothing but this, the same OR gate symbol, but you put a dot or a circle in front of it. That is a NOR gate. De Morgan says that if you have A plus B whole bar, you can separate the bars A bar and B bar, and you put a AND operation or a dot operation in front of it. That is one and the same. Okay. Most of the problems can be solved using symbol Boolean algebra. Very rarely you might need truth tables. Sometimes you might have to track the inputs, how they are going to give you specific outputs. Let's have a look at the last couple of questions before your chemistry lecture will start. Here is your first question on your screen. For the circuit above, what is the equivalent gate going to be? Okay, what is that equivalent gate going to be? You have multiple options. You can use Boolean algebra, or if you feel like, no, sir, I don't want that. I want to, solve it using truth table. Anything is fine. Okay, it's completely up to you. What do you think it is equivalent to? First of all, at this particular point, as you can see, this is A dot B and this is bar of it. This is AND with a NOT, so I'm putting bar. This is a OR with a NOT, so this is a NOR operation. So this is A plus B and this is whole bar. Okay, this is nothing but a NAND operation. So this output will be, you take A dot B whole bar, you take A plus B whole bar, NANDing it, that means you put a dot symbol and then you put a big bar on both of them. That is what this entire operation is at the end of the day. Correct, everyone? So if you want, you can also rewrite this particular thing as this whole bar is there. A dot B, I can write it as A bar plus B bar. This is dot. And this thing over here, this thing over here is nothing but A dot B, and this is A bar separate and B bar separate. That is how it will look like. This is one way of doing it, but it is not leading us to anywhere. So I have an idea. Why not separate this big bar into two separate entities using De Morgan? So I have A dot B bar. I have A plus B bar. I take that big bar and separate it into two entities. This dot will now become a plus. That's what De Morgan is. Bar bar will cancel out. Bar bar will cancel out. So this will become A dot B plus A plus B. A dot B plus A plus B. Is that right? So what do you do next? A dot B plus A plus B, guys. Come on. Now it is a much simpler operation if you think about it. It's a much simpler operation. Okay. And now if you want, you can use your truth table and solve it, or you can still simplify it if you want. Like take A common. This will become B plus 1 and plus B is there. Okay. Now what is B plus 1? What is B plus 1? See, for example, B is 0 or B is 1. So what will be B plus 1 equal to? Look at it. B plus 1. 0 plus 1. 0 plus 1 will become 1. 1 plus 1 will not become 2. Don't say 2. 1 plus 1 means 1 or 1. The answer is still a 1. So the output is always a 1. So B plus 1 actually makes me get how much? Just 1. All right. Now what is A dot 1? A dot 1 is just an A. So it will become A plus B. This plus stands for OR gate. So the answer is an OR gate. So using Boolean algebra, it becomes easier. Else you have that headache of truth table, all the possibilities you have to think about it, which is scary. Let's go to the next one on your screen. Identify the logic gate given in the circuit. Okay, let's do this. This is A, naturally this is A bar. This is B, naturally this is B bar. This is a AND operation. So it is A bar dot B bar. There is a circle also, and that means you have to put a bar over here because this is a NAND gate. So again use De Morgan principle. A bar, B bar, you separate it. Separate that big bar separately. Convert that dot into plus. A bar bar is A, B bar bar is B. A plus B is nothing but a simple OR gate. That is the answer. So De Morgan becomes very, very handy. All right. Let's go to one more question, guys, coming up on your screen, and here it is. Let's see if we can solve this. Consider the following circuit. When do you think the output is a 0? When do you think the output is a 0? Let's think. Reverse. This gate is basically a NAND gate. Okay. So think of it like this. This gate is basically a NAND gate. That means this is what it is. This is your Y. I want my output to be a 0. That means this point should be a 1. And this can be only a 1 if this is 1 and this is 1. That means this should be 1 and this should be also 1. This is a AND gate. AND gate is a 1 only if A is 1 and B is 1. So like that, there is only one option, which is the first one. That's it. There you go. That's how easy it is to solve the question. A lot of people waste time writing the truth table, which is not needed at all. Next question on your screen, here it is. Which of the following circuit has the same output as that of the given circuit? Again, if you want, you can again make the truth table or use Boolean algebra, whichever you find it comfortable. But like I said, truth table might take some time. It's completely up to you how you want to solve it. Come on, my dear students. What are you going to do? Yeah, try to take it up as homework because we are a little bit out of time. Chemistry lecture has to start. Just try it out. Answer is there on the next slide. You can be able to easily figure it out. Just giving you a couple of hints. This is A, this is B, right? So this is A, this is B bar, this is A, this is B, this is nothing but A dot B bar, this is nothing but A dot B, this is a OR gate with a NOT on it. So technically this is A dot B bar, A dot B over here, and you're ORing it. That means you're putting a plus and then putting that circle means knotting it. This is what that operation is. Simplify it, you will get a very, very laddu answer. And then you will be surprised to see, oh my God, it is such a laddu question. Okay, just try to solve this particular question. It is not difficult. I can give you some hints. You can take A common also. Once you take A common, it becomes very, very simple. So it will become A dot B bar plus B. So that's it. This is your hint. After this, you figure it out. Okay. The answer is there on the next slide. Right. So that's it from today's class. I hope you enjoyed it. Revise semiconductors and logic gates like never before in a very crisp, concise, and short manner. Bye bye. Take care. Have a great time.